Hello, Assalamualaikum.
Salam doktor.
Waalaikumsalam.
Okay. Group number,
Group number 1.
model,
Model A.
members, name,
Uh,
Haziq,
me, doctor.
Haziq Fadila.
Yes, doctor. Hello, doctor.
Yeah.
Sorry.
Tamimi,
Ni doktor.
Ta, Tamimi Shah.
Yes doktor.
Satu lagi. ITS. Siapa tu? ITS. It's. Nama siapa nama? ITS.
Muhammad Nur Arif Farhan. Sorry
Hai.
doktor, saya tak reti nak. First time saya guna Zoom.
First time. Orang dah berzaman dah pakai Zoom. Kau baru first time. Dalam zaman kau ni. Yasir Fakir.
Yes, doctor.
كيف حالك؟
الحمد لله.
كل خير.
كله بخير.
Alhamdulillah. Okay, start. Share slide.
Ya, doctor. Notes.
Try again.
Way to share screen, doctor.
Hmm.
Way to share the screen.
Try again. I already enable.
Hazik, to share the screen, it's beside the chat. Down.
Bisa dicek.
Yeah, beside chat. Down. It's
Oh,
green.
green. Sorry. Can you see my screen, doctor?
Yes. Slideshow.
Okay.
Slideshow.
Okay. Assalamualaikum and good evening to Dr. Fuad. Today, we are Group 1. We present about Model A, title Analysis and Control of an Industrial Hydraulic Actuator, which consists of me, Haziq Fadila, Muhammad Tamimi Shah, Bihelmi Shamza, Yasir Fakih, and Muhammad Nur Arif Farhan bin Shahrin. This presentation will start from Tamimi will introduce about introduction.
Next slide. Okay, thank you Haziq. So here, this is introduction for our presentation, which is this presentation focus on hydraulic actuator system, specifically electro-hydraulic actuator EHA system. This system are widely used in applications such as robotic, aircraft, manufacturing due to their fast response capabilities. However, they are inherently complex and exhibit strong nonlinear behavior. Therefore, developing an accurate and solid system model is essential to ensure effective and reliable control. Next. Okay, so here for our assignment that we use the model A, the damping using 45 milliseconds. So our data which is have input voltage and output displacement in millimeter. So the tool that we use to apply the system identification, which is MATLAB System Identification Toolbox, pre-processing tools, and model validation tools. Next. So in this case, why we use the PID, which is PID stands for proportional integrate derivative. This is to make the system performance target that we need to have a fast response, lower than 10% overshoot, zero steady state error, and also stable. So we use MATLAB and Simulink for design and testing. Next. So from our assignment that we have a proper statement that a complex behavior such as friction and nonlinear flow characteristic, and also the system may have slow response, steady state error, and also instability. Next. So based on our objective for the assignment, it is we need to model the system under consideration, which is we need to do steady state error and also ensure that the system is stable. Next. Next. So for our scope and limitation, which is for our model data, which is we only focus on model A data set, and also we only use the time domain and frequency domain for our assignment. Then we need to design the PD, and also PID controller to make the specification. We also need to use the PID tuner for response tuning, and also for our simulation, which is only limited to MATLAB and Simulink. So I will pass the slide to Haziq.
For the methodology and approach, first one, we will do the system identification, which is the system identification toolbox. And the second step, we import the data, which is model A. The sample is 45 millisecond. And then the data processing, where we will remove the mean and we select the range, which is we split into two, 50% for the estimation and 50% for the validation. And the system analysis, we analyze the open loop behavior, such as the pole and zero map and step response. And then from the open loop, we construct or build the closed loop system by using unity feedback. We analyze the transient, peak time, settling time, and others, and overshoot. And then after we do the system analysis, we do the controller design. We design the P controller, PD controller, and PID controller. And then we use the rule locus for pole placement and tune gain manually and with Simulink. And for the sixth step is simulation and tuning. We develop system in Simulink. We apply the PID tuner to refine gain value and verify response through step input test. And the last one is performance evaluation. We compare the uncompensated and the compensated system, and we see how the control effectiveness in meeting the design spec. Okay. First one is for modeling. This one is for the task 1 and task 2. The empirical modeling, we start with model data, and then we do the system identification toolbox MATLAB, pre-process data, remove mean, and select range. For the model A, they are 1,200 samples. So we do the 50% of estimation is from 1 until 600. And then for the 50% of validation, 601 until 1,200. And then we test the pole zero combination. After doing the pole zero test, we all of our group agree that we will choose the 3 poles and 2 zero. And then select best model. Best fit is around 97% and it is stable. After that, we obtain the transfer function. Okay. For the open loop system, for the continuous time transfer function, triples 20, our open loop system is negative 1.155 s squared plus 333 and 6s minus 1.052 divided by s cubed plus 56.21 s squared plus 0.005923 s plus 0.3329. From this open loop system, our value for the zeros is negative 28 and 288 and add to 80 and negative 0.0032. Meanwhile, for the pulse, negative 56.21 plus 0 G imaginary minus negative 0 real plus 0.077 imaginary. And the last one is negative real minus 0.077 imaginary, and the system is stable. For the closed loop, we use the formula Ts or equal to Gs over 1 plus Gs, which will be equal to 1.155 S square plus 333.6 S plus minus 1.052 divided by S cube plus 55.05 S square plus 333.6 S minus 0.7191. For the analysis for closed loop system, the rest time is 0.3202 second, the settling time 0.57925 second, overshoot 0, peak time equals to 1 second, and the steady state error is 0.0023792. Yeah. For the discussion, as you can see, the top one is the show the best fit line percentage. We got the 97.92% for the triples and 2-0, which is higher than minimum 80%, and the system behavior is represented very well by the model. And the bottom one is showing the frequency response. Frequency response shows the magnitude graph show a big spike, and the phase graph drops quickly. And next slide is showing the open loop. The top one is open loop step response. It is high frequency of oscillation, but the system is stable. And the bottom one shows open loop pulse and zero map. It is 3 pulse and 2-0. The system is stable because all pulse is on the left hand plane, and the pulse move as gain varies. Potential gain adjustment to enhance the system performance. And this one is for closed loop system. The top one shows closed loop step response. It have the parameters such as peak time, settling time, and resting time. Meanwhile, for the bottom one shows the closed loop pulse and zero map. You have 3 pulse and 2-0. The system is stable, and it is type 1 system because there is value on the origin for the zeros. Next is the Simulink for the task 2. This is the Simulink block for the closed loop system. This Simulink block is to compare the closed loop step response graph from the Simulink and the generated from coding. This is the graph that we got based on the Simulink graph. Okay, next I will pass to Arif to continue the slide presentation.
I analyzed the root locus of the system. We plot it by varying the gain K. The plot shows how the closed loop poles move as K change. In this case, we select the K equal to 40. At this value, all poles are in the left half of the S-plane, so the system is stable. However, I noticed that some poles are quite close to the imaginary axis, which could lead to oscillation or slow damping. Next. I generate the open loop book plot for K equal to 40. From the plot, I obtain a gain margin of 1.70 dB at 127.42 radian per second, and a phase margin of 4.96 degrees at 113.32 radian per second. These margins are low. Ideally, we want a gain margin above 6 dB and a phase margin above 55 degree for good robustness. This tells us that the system is quite sensitive to additional gain or phase lag, and could become unstable. Next. Then I plot the closed loop book plot to study how the system responds across frequencies. The peak magnitude is 12.43 at 115.30 radian per second, and the estimate bandwidth is above 199.95 radian per second. This gives us an idea of frequency range where the system can effectively operate. Next. Okay, last. I load the closed loop state response. The rise time is very fast at 0.00881 seconds, but the overshoot is 92%, which is very high. This indicates the system is underdamped and may have excessive oscillations. The settling time is around 0.88 seconds, which is acceptable but could be improved with better damping. That's all from me.
All right, so for my part, I did the PD controller design. So this is the root locus with the gain K equals 40, and we also have the root locus for the closed loop after the PD compensated. With KP, we used KP 15 and also KD 0.1570. Next. As you can see, this is the uncompensated system on the left side, and on the right side, this is the after timesing it with the PD controller. So we wanted the overshoot under 10, and we also wanted the settling time to be slow as possible. So our PD controller became after the PD controller, the system became lower overshoot, so it's 7.6, and settling time is 0.06. Next. So the high value of KP will reduce the rise time, but it also increases the overshoot and reduce the state error. But the high value of KD will also reduce the overshoot and improve stamping and increase stability. Next. This the Simulink for the PD controller. And then next. Yes, this the graph. As you can see, the overshoot is the time for it to be stable is quicker than before, and the overshoot is a bit less than before. Next. So the step response that we just showed, it will show the value overshoot and settling time decrease, and the system demonstrate a step response behavior equivalent to the MATLAB programming. And Simulink work as an alternative way than use the programming in MATLAB. And that's all. I'll pass it to Timon.
Based on the PD, we can use the PID controller to improve our steady state error. So here our Simulink diagram for PID controller that we use the value using the PD, which is KP equal to 15, and also the KD is 0.1570. Next. So here we get the same as the PD controller as we use the same value for PD design. So next. So to achieve a better output or better achievement in our graph, so we need to tune the KP, KI, and KD. So we will use the tuner on the MATLAB to tune the output. So next. So this is the MATLAB coding that we use to tune the PID controller, but this is the assumption value for the KP, KI, and also the KD. So next. So when we use the MATLAB coding, that we need to manually insert the value to find the desired output. Instead of that, maybe we can use the tuner on the Simulink that PID effectiveness that can have better. So see the comparison between the uncompensated response and compensated response. Next. So here we use the PID tuner on the MATLAB that we can see the graph that we get the beta which is in the overshoot is become lower, which is 7.66%, and also the crossroad become stable and also we achieve the steady state become 0. So next. So based on our solution for the PID tuner that we already achieved the system for a faster time, STR, and also the overshoot become lower than 10%, which is 7.66%, and also the system is stable and the zero steady state error. So we can conclude that our system already achieved all the objectives that we want in the assignment. So that's all from our group. Thank you.
Okay. Thank you. Who is the leader?
Me Doctor.
Name.
Hazif Fadilah.
Zik.
Yeah,
Ni model A.
yeah.
What is the mathematical model dia from system ID?
Computer from system. This one Doctor.
How many poles? How many zeros?
3 poles and 2 zero.
3 poles and 2 zero. What is
Yeah.
the best fit?
Best fit is 97.92%.
57.92%. Tamimi, can you show the poles and zero location?
I need to show on share screen, Doctor.
You ask the
Okay, that's the pole and zero.
poles and zero map.
You can see that the two
I cannot see. Poles and zero map.
Wait Doctor.
Dalam report ada tak?
Ada Doctor.
the Doctor tengah tunjuk.
Ni. Sensor. Shows on the map or the value Doctor?
On the map. Tak nampak. Oh. 3 poles, 2 zeros. Tengok value. Value. Ah. Oh, jauh Okay. Can I see the siapa ni? Yasir. Yasir Fakih.
Yes, Doctor.
What is the settling time and steady state error before controller design?
Before the PD. Before the PD.
Before controller design.
Oh, before the conference. Next.
There. Analyst closed loop system.
Yeah. What do you need, Doctor? Which
Slide nombor 12 tu. Rise time
uh
0.32 second.
0.32 and the
Steady
setting time 0.57925 seconds.
So after controller design, what is the rise time and steady state error? After
After
controller design.
yes. After controller design,
What is the settling time and steady state error?
settling time is 0.06, and after the VIT controller, it's zero. The steady state error, the error is zero.
Okay. Who is the other guy?
Arif Doctor.
Huh?
Arif Doctor.
Arif. Yang Arif. Prof nak tanya. Tengok code, ada code tak? MATLAB code.
MATLAB code.
Share MATLAB code ada tak dalam?
For which task Doctor?
All lah.
All because
You didn't share.
we do the separate task.
You have to insert lah inside your report the MATLAB codes.
Oh.
Nanti submit balik via email. Okay. Share
Okay.
the MATLAB codes that you have now.
Share screen kat sini ada ke hantar kat email?
Share kat sini. Share the MATLAB code here. Besar sikit, tak nampak. Arif, print F tu apa?
F nak display.
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 Display status the error tu.
Okay. Kod lain? Kod lain?
Ya,
Kod yang lain.
kod yang lain. Uh,
Can you share any other codes? Aziz, ada kod lain tak?
Macam ada. Share yang task tu.
Klik lah atas tu. Tu. Hmm. Slow. Okay. Browse. Okay, stop. Arif, PZ map line 29.
29.
PZ map bracket G. What is that?
Untuk whole zero map.
English.
For the plot the whole zero map.
Location on S-plane.
Location
Location of pole and zero on S-plane.
on whole zero map.
Okay, browse. Slowly. Okay, this loop is for what, Haziq? The loop. If all display, else display.
Open loop dah tu. Open loop.
Apa benda tu?
Open loop system.
Bukan, dia punya looping ni untuk apa?
Ya tu. Yang stability check ni.
Oh, stability check.
Ya.
Kalau dia real less than tu display, else. Okay. Dia check lah.
Ya tu.
Next, setelah apa browse lagi bawah.
Ini untuk open, yang ni untuk close.
Close.
Yang ni untuk closed loop system.
Okay, any other codes?
Maybe time ini can share.
Never mind, code dia masuk dalam report lah. Mana boleh keluar. Kan tak nampak.
Okay, dah.
Sebab dia ada markah untuk kod. Kalau dia tak masuk kod, maknanya tak ada markah. Okay, thank you very much for the presentations.
Yeah.
Okay, you may exit. Other group will enter.
Okay, thank you very much.
Thank you, Doctor.
Email
Thank you, Doctor.
the report.
Okay, dah.
On video. Munim, on video. Group number.
Sorry, group 5.
Model
Okay.
CD.
Model A.
Munim, on video. Munim. Okay, you can start.
So we can start now.
Yes.
Okay. All right. So I may continue.
Yeah.
Okay, then I'll continue first. So we are from group 5 and we are doing the analysis and control of industrial hydraulic actuator model A. So my name is Lizishan A23K0521 and I'm the leader of group 5. Then the next three members are Amirul Mirza, Sheikh Muhammad, and also Abdul Munim. So later on, they will further introduce themselves later when reaching their state, when reaching their floor. So this is a table of contents for our presentation. So by today, you'll get to know the introduction, problem statement, objectives, scopes and limitations, and task 1 until task 5, and lastly is the reference for our projects. So first of all, I'd like to introduce to all of you about our assignment. So the system under, sorry, I think, please. So the system under studies is actually an industrial electro-hydraulic actuator that is commonly used in aerospace, robotics, and manufacturing, and etc. So for our case, we are actually doing industrial hydraulic actuator, which is also known as EHA. It's a bidirectional hydraulic cylinder with a position transducer and also a proportional valve. So in our model, in our assignment, the input will be the voltage and output will be how many displacement that the hydraulic actuator can go. So in our assignment, we will be doing system identification. So this step is for us to develop a mathematical model from experimental input and output data that given by SIR, which is written as a model A then. And next we'll need to do the models, which is system is represented using a continuous time transfer function model that we develop from system identification. And the model is will be estimated by fitting to the real data, and also we analyze accuracy in terms of the best fit percentage, pulse and zero, and frequency response. That will later on present by Munim in the task 1. And next thing to say about is the system identification procedures. So basically, what we'll do is we import the data into MATLAB and we remove mean and select data range, and we're splitting data into estimation and validation sets and choosing models, number of poles and zero. Lastly, estimate the transfer function model. This one is also in task 1 will be further explained by William. And the tools to apply system identification is we implement the MATLAB system identification toolbox. So after we've done this, we're going to tuning the PID controller. So before I'm moving into PID controller, I'll just introduce a little bit about PD controller. It's used to improve transient response. It's also maintaining the steady state error. Yeah, it's PD controller, what PD controller does. And PID controller is PI plus PD together, and it's implemented to improve the steady state error and also transient response independently. So the more details of designing this will be further explained in task 4 and task 5. And the PID tuner MATLAB we'll be using is a PID tuner in Simulink, and is used for automatic tuning of the PID gain. So in our assignment for this one, model A, the problem statement that we find is the hydraulic actuator system is difficult to control due to nonlinear behavior. So a mathematical and a legit transfer function model is needed to understand and so that we can control the system accurately. As we know that manual modeling is very hard, like we can't really manual modeling it. So that's why we need the help of MATLAB MATLAB application, the system identification tool using real data. And the PID controller in our assignment has certain specifications to meet. So some of the specifications are fast responses and overshoot of less than 10%, zero steady state error, and also stable system. So the next objectives, I will pass the floor to Shed.
But I think Seth is not in the meeting yet.
Oh, really? He's not in the meeting. Okay, all right. It's okay. Then I'll continue the presentation. Sorry for the late of our members.
Who is,
So the next thing will be, sorry,
who is the members? The other one?
it's
Syed Harsham.
actually Sheikh Muhammad Harith Shah.
Dia pergi mana?
Sorry,
Dia pergi mana?
dia di mana?
Hmm.
Reply
Uh,
letter dia.
Huh? Munir, your friend.
Yes. Yes.
Call your friend. The other one.
Okay. I will call him.
okay, asking him in the group ready. He said, wait, he needs some time.
What is his name?
Sheikh Muhammad Harith Shah, the third person.
Okay.
Yeah. I'll continue with the presentation first. So the next thing, the objectives of our assignment is actually to model the system under consideration. So what are the consideration? We need to design the PID controller, which has a fast response whereby reaching a desired position as fast as possible. We didn't have like a fixed value to say we need to reach how much value. We just need to have a fast response as fast as possible. And we also need to achieve an overshoot of less than 10%, and also zero steady state error. And lastly, we need to ensure that our system is designed to fully stable. So for the scopes and limitations for our assignments, we do admit that there are some limitation. So our models is actually derived using data sampled at a specific intervals, only like 45 milliseconds for our model A lah. And also the analysis is limited to provided data sets of only 1,200. So this is our limitations. And our scopes is some of them are we are using only input responses for our system identification and controller design. And also our system, we are assumed to be linear and time invariant. And lastly, we assume that it's unity feedback configuration according to the instruction in our assignment. So that's our scopes and limitations. And next, I'll pass the floor to Munir to present about task 1.
All right. Assalamu alaikum. As we can see here, we start with doing the modeling. Like we can get our design in mathematical set. As we can see, we use the system identification tools. First of all, we just take the value and take out the mean. We take out the mean because of the DC offset that getting from the sensors. Then after taking out the means, we start dividing the data to estimation and validation. And then we start with the transfer function estimating with the estimating value. And in the transfer function, we have two choices. One of them was 2 poles and 0 zeros. And this one will get us like 80%. And we tried also for 3 poles and 1 zeros. Yes, for 3 poles and 1 zero. And the benefit to get the 2 poles and 0 zeros, then the 2 poles times bonds is better. So we don't need the PID tuners anymore. But if we use the 3 poles and 1 zeros, we will use the PID tuner. So if we choose the first one, we are going to save more cost. Also, after getting the right estimation value, then we proceed to get the time response and the frequency response and to see the transient response as well. And the overshoot and the pulse and zeros location, as you can see in the slides. Can you change the slides? Yes, pulse and zeros map for the open loop system. Change. and that's for the modeling part.
Okay. Thank you, Abdul Munim, for the task one presentation. And then we will continue to task two, which is the analysis of open loop system, where in task two, we try to analyze the system by using MATLAB code. Like we try to get the how many poles and zeros in the system, and we derive the open loop transfer function and closed loop transfer function from the MATLAB code. And then we produce a pole zero map to see if the system is stable or not. And can the next slide, please. And this is the product of the MATLAB code, where the open loop transfer function is shown there. And in the open loop zeros, we can confirm that there is no zeros, and then there is only two open loop poles. And then from the closed loop transfer function, where that we analyze in the MATLAB, we can see that it it produce the closed loop time response characteristic shown there. At the rise time is 0.2996, settling time 0.5345 second, peak time is 0.8873, and the overshoot is 0.0%, and the steady state error is 0. So this shows so in the pole zero map of the open loop system, it showed that all poles are on the left half plane, which is stable. The system is stable. And then from the closed loop time response, we see here that the rise time is around like 0.3, which is fast, but not too not too jumpy or not too aggressive. And the settling time is just 0.535 second, which is just over half second from the rise time, meaning the system is stabilized very quickly. And shown here that the system the overshoot is 0%, which is most impressive lah. But because this is I can say that this is the solid baseline that we can use to design and tuning in of the PID controller. And then wait. Yeah, I think next slide.
Just to add on here, we get zero steady state error is because we are using step input for type 1 system. Our two poles and 0, 0 system is type 1 system, so that's why our steady state error is 0.
Yes. And then this is this Simulink model. The same model that we did using the same model, and the dynamic characteristic of hydraulic actuator system. And here that we confirm that the rise time is actually 0.3 and the settling time is 0.535. And then it I think peak at at 0.8. up to 0.8. Yeah. So yes, this is actually is the baseline for our next task, which is the closed loop system analysis for and tuning the PID controller. I think I I give floor to the next person, which is Reza for task 3. Thank you.
Okay. Hello everyone. Wait a minute. I'm sorry, doctor, for late because I just miss see the timing. I thought. I'm sorry about that. So first is for task 3 is about plotting the root locus. So here is our root locus for our system. So our system is a second order system. So here we are using uh, two poles and wait, two four poles, one zeros.
2 poles, 0, 0, no 0.
Ah,
2 poles
okay,
only.
okay. Two poles and no zeros. So it is stable for O value of K. So for the next slide is also response here is yeah. So we can see the gain here is 2.39 for the gain that we will use later. So in the next slide, so here is our open loop bot plot. So for the second question in the task number 3 is for plotting a bot plot for open loop. So we are using the gain k 2 k equal 2.39. So as we can see here, so the system are stable and the phase margin for this system is 65 degree and the gain margin is infinity. So for the system are stable, gain margin and phase margin, since gain margin and phase margin are positive. So for the next slide is for a closed loop bot plot. So we are using gain equal to k equal to 2.39. So for closed loop bot plot, so our phase margin is 161, and then our gain margin for gain margin for k equal to 2.39 is 0 dB. And then so to
20
find
log ME is 0.
20 magnitude peak, I'm sorry. So magnitude peak is 0 dB, 20 log. So magnitude peak is equal to 1. And then so we observe at the plot, so we get the peak frequency 2.96 radian per second. And to know the bandwidth frequency, we tap at negative 3 dB, and then we find out the bandwidth frequency is equal to 19.4 radian per second. So the system is unconditionally stable. So next is I will pass to Lee.
Yeah. So, previous tasks, we have convinced ourselves that the both results in time and frequency domains are identical in terms of their stability property. So, in the next task, which is task 4, it's about PID controller design using root locus. So, this is the PD controller design specification that I I plan to achieve. So the new design spec, I plan to reduce the rise time from 0.3 to less than 0.08 second. And the percentage overshoot, I aim to maintain it maintain equals to 0 lah. And then the settling time reduced by fourfold, which is new one, I aim to be it 0.13 second. So this is a manual calculation I proposed to find our PD controller design. So just using the formula to get to find or to prove that the steady state error is equal to 0, which is I mentioned just now. And then the TS new we aim to have is 0.134. So using the formula, I can obtain the real part of our closed loop, our new another closed loop code for the angle criteria. So the real part is here. And then the imaginary part is also same, using the real part equals to zeta omega n. And by using mathematics, shifting left and shifting right, by using plus minus and also square root square, I got the value, final value is J 14.46. So the final value for our closed loop pole for the next step is negative 29.85 plus J 14.46. So this is a value here. And then in order to find the zero value, the new zero value that we should add in for our PD controller design, we're using angle criteria formula, angle criteria method. So we just, we know that poles, if the angle of poles is plus and then angle of 0 is minus, so we got that negative, the theta 3 is 75.3 degree. So by using trigo formula, angle, the triangle here, we got that the x here, the value in between 27 to negative z is 3.8. So the final value for the 0 is negative 33.65. So now we have known that the 0 is negative 33.65. So we find the k value by using this formula, which is poles over 0 formula. And the gain value that we got is 32.704. Then to find the KD and KP, we know that S plus KP over KD is equals to, this one 0 is actually equals to KP over KD. So in order to find the KD first, we use K equals to 157 multiplied with KD, because 157 is the value from our transfer function, the gain value. So we got that KD is 0.208. And then we substitute inside the 0 formula here. We got that KB is equals to 6.999. So our final GPDS GS transfer function is this, as stated here. So moving on to the next step, we are now want to analyze the root locus. So we put the value that I gained just now inside here. So this is the PD controller KD multiplied with S plus Z that I mentioned just now. And then we multiply with our transfer function here. And then this is our open loop system. And then we use open loop system to plot our root locus. So this is what we got for the root locus. And clearly it's shown that the point negative 29.85 plus J 14.46 is exists on our root locus. So in the assignment instruction, we are also required to enhance the simulating block diagram from task 2. So this is how we enhance it. We implement the PD controller design inside our system. So this is the specification that I obtained just now. I put inside the PD controller specification here, the block parameter, and then I also inserted input probation and output measurement in the Simulink to check so that I can block in the linear step response characteristic. So this is the Simulink time response after adding PD controller. So it's clearly shown that the settling time is 0.0804 second, and the rise time is 0.0534 second. And however, for overshoot, it slightly improves a little bit, but it is still within 10%. So from here, we can still clearly see that it's stable. And from task 2 and task 3, since we have knew that we have zero steady state error, so we no need any PI controller. And this one is a time response comparison between task 4 uncompensated and, task 2 uncompensated and task 4 compensated. So for settling time, we managed to increase the settling to reduce the settling time up, means become faster. And also rise time is become faster as well. Just that the overshoot is rise a little bit, but it is still considered a good design because it's within 10% within the requirement. So moving on to the task 5 is about tuning of PID gains. So we are required to tune the PID using the Simulink as well. But this time we use the auto tune. We are not like manual calculation by ourselves. So this is the tuning PID controller that we believe it is good for our design. So we go to see the performance and robustness first. As you can see, the rise time here is 0.0416 seconds, and the settling time is 0.0661 second, which is even better. And also overshoot, clearly we see that it's 0.6%. So it is slightly lesser than 1%. So it's even better than task 4 lah. Yeah. So to achieve this performance and robustness, the controller parameters suggested by the PID tuner Simulink is as such. P with 9.0744 and I, we don't care because we don't need any PI controller. And the D value is 0.29524 and N is 5501.671. So this is a proof that, we're actually tuning here. This is a reference track. So this one with solid line is our tune response. So by extracting the value that I gained just now, I put inside the PD controller here as such, labeled here. And also I check again the linear step response characteristic. So this is what I got for my final task for Simulink time response for task 5. So I can say that we successfully even improve our time response from task 4. So the settling time is 0.0661, which is even better than task 4 of 0.08. And then rise time is 0.0416, even better than task 4. And also percentage overshoot, we managed to reduce a little bit. And it's still, it's lesser than task 4. At the same time, it's lesser than 10% of overshoot. So in conclusion, I can say that the transfer function model that we make using system identification is 2 post 0, 0. We have achieved a very, I can say, quite good time response, but we can even go for better one. So we did the PID tuner gain, and clearly we see that it's even reduced until fast response until this. So that's all for our task 1 until task 5, and also our presentation. And lastly, we have successfully achieved all the specification in problem statement and also objectives. So lastly, this is our references for our assignment.
What is the mathematical model for this case?
Okay. The mathematical model is this one. 157 over s power 2 plus 27.03 s plus this one, because it's relatively very small. So in further analysis, all of us assume it to be 0.
Okay. What is the best fit, Amirza?
Sorry, the best fit result is
It is 80.36.
Huh?
80.36.
Okay.
yeah, 80.36%. And so we have fulfilled the best fit because the requirement is 80%.
Side, What is the value of error, steady state error, and settling time before design controller?
What are the
What is the steady state error and
state,
settling time before controller design?
settling time is 0.5345 and steady state error is 0.
What is the value of the settling time after controller design?
After slide is 0.0804 and overshoot. Settling time 0.0804 second.
Name,
Yes.
show me some code in the slides. MATLAB codes.
Okay.
Oh, just now.
Sorry, sir. Which code?
Yang tadi tu, just now. Oh,
Oh, this
can you make it bigger?
make it bigger. Okay. Wait, okay. Is it big enough? Okay.
Munim, what is line 15?
Doctor.
Line 15.
Line 15. You want the PZ map?
What is the function of PZ map?
The function is to get the plus and zeros map.
Let's plan.
Plus and zeros map.
Can I see on the right, please? On the right. Munim, what is feedback bracket G, comma 1? What is 1 stands for?
Again, Doctor.
Line number 42.
Number 42. It should be for
Bigger.
this number.
42. Feedback bracket G, 1 bracket. What is the 1 stands for?
One should be stand for time. Visualize.
Sorry?
Yes, I'm gonna try to remember. The feedback for gain. Okay, for the gain to be 1.
Sorry?
The value of the gain.
The value of the gain.
The gain, yes.
Okay. Xian, what is the break 1 stands for in the feedback command?
In this line 42 is actually unity feedback of 1. Means feedback 1.
Unity
Yes,
feedback.
yes. I mean the feedback gen. The feedback gen.
Yeah. Okay.
Yes.
Next, smaller. Xian, yang tadi tu? No.
Which slide, sir?
Tadi, slide, code slide.
Or the one code slide? Okay.
Bigger. Bottom right.
Bottom left, right here.
Okay. Line 58. What is ABS? Line 58. Xian.
Oh, you're asking me. Means absolute value. Because this one is we want to find the steady state error using the MATLAB code.
I know, but what is the function of ABS?
Absolute is actually making to an absolute value, which is like a readable value in linear one. Like steady state error. Yes.
If in the bracket is +1, what is the absolute value?
Sorry, positive what?
If ABS bracket 1, what is the value? ABS bracket 1.
Absolute 1 will become 1.
If the absolute bracket -1, what is the steady state error?
Absolute bracket minus one.
Uh,
To be honest, I didn't try it before lah, but I believe it might get one as well.
uh,
Uh,
yep. Yeah, you get one. It's like it's like it's
yeah,
a positive value. It's a positive value.
yeah. Because I never thought of using absolute minus one. Sorry, didn't think of that.
Who wrote this? Who wrote this program?
Oh, this one.
Ah,
This one is by task two is
That's
sorry.
two.
Task two is by oh yeah, me
Amirul.
yeah.
Yes, me.
you're supposed to know what? It's a team effort kan. Mana boleh silo. Next code. Next code.
Next code or next MATLAB code is it?
Ah, yeah.
Okay, this one.
Bigger.
Can see.
Browse.
Sorry.
Browse.
Browse.
Browse. Lagi bawah.
Browse to
Bawah lagi. Okay. Why this one ESS? There is no absolute. ESS equal to 1 minus DC gain. Why is not absolute? The previous one was absolute, but this one no absolute.
Because actually from task two put absolute, but then in task four I found out that because I thought I get the result from task two, then it's zero. So I just don't care if put absolute or not, because no matter you absolute zero or no absolute zeros, it also will get zero. So that's why I didn't put absolute there. Yeah. I know. Yeah. Uh, mm. Yeah, but this one is for our case lah, because our case is steady state error equals to zero. Yeah, but for other cases that might be different. So that's why for my case I didn't put absolute in task form.
Okay, thank you very much. Thank you very much.
Okay, thank you, Doctor.
You may exit.
Thank you, doctor.
Thank you, Doctor.
Thank you, doctor.
Did you email the slide already?
Sorry?
Did you email the slide already?
Oh yeah, about regarding the slides, sir, we actually made some amendment on the slide. Is it possible for us to resend a new one?
Yeah, send a new one.
Yay. Okay. Thank you so much, sir.
Please fill up EPPK. Munem. EPPK. Teaching Evaluation. Amirul Mirza, dah isi belum? Syed? Syed?
Ya, Doktor.
Dah isi belum?
Belum, Doktor. Saya isi sekarang, Doktor.
Okay. Munim, have you fill up?
Doctor, not yet.
Teaching Evaluation. Huh?
Yeah.
Okay.
Not yet, not yet.
After this. Shian sudah. Have you fill up, Shian?
Saya sudah.
Okay. Okay, you may exit.
Thank you,
Thank
doctor.
you, Doctor.
Next group.
Yeah.
On video.
Doctor, my camera isn't work.
Sorry?
My camera stopped working right now.
Using handphone.
Can use handphone? Okay.
Group number. Hello, group number.
Assalamualaikum, doctor. Dr. Sad's camera is not working.
Group number. Bye.
Group number 4, doctor.
Char.
Doctor, can you hear me?
Char. Char number. Ek number. Char number. Masfik. Char number.
Yes, doctor. Star number.
Model. A, B, C, D.
LD, doctor.
Huh?
ED.
B.
D.
Yes.
Boy. B for boy.
D, donkey.
D. Oh, D. Model D. Saja.
Doctor, can we start?
Saja Magdi.
Wait for a second.
Doctor, I'm waiting for you to accept.
Oh, okay. Here, I admit you. Abu Bakar Halim. How many groups? Abu Bakar is 4 p.m. man. Okay, this microphone. Echo. Okay, start.
Can anyone of you share the screen? I need to let it come out.
Okay, I share the screen.
Yeah.
Okay.
Okay, I will start. Assalamu alaikum wa rahmatullah. We are group 4. I'm Sajamidi Salahuddin. My group member is Nasir Mahmoud, Nasir Dirwish, Mahmoud Mashfiq, Muhammad Sheikh Kwan. Our project is about hot air blower system P23236. So first, I'm gonna with the introduction about the system. Thus, the system is about a laboratory scale of thermal process control system used to study the dynamic of heating and temperature. It consists of heater and fan that put the heated air to channel where the temperature is measured by a sensor. This system is known for its time delay and thermal lag and slow response. We have to find like a solution for this problem. We use a control system design. In our project, we use MATLAB and Simulink to analyze and control this system. The main step is including that collecting temperature data and analyzing to collect temperature data, developing mathematical model using system identification, analyze open loop behavior, and design the PD and PID controller to improve the system performance. The MATLAB tools used is the identification toolbox and control system toolbox, Simulink, and PID and PD tuner. Our goal is to design a control that ensures that the system is stable and we have a fast response and in the closed loop system. So why we need to use the control here? Because we have a slow response and overshoot and the temperature is not, and the system is not stable. So the tool is used is MATLAB to handling the data and modeling, system identification, and Simulink and PID tuner. What we are going to do, we are going to collect and analyze data, model the system PID, and analyze open loop behavior, design PD and PID controller, simulate and validate results. What we are expect to achieve, we achieve like a fast response, low overshoot, zero steady state error, and stable system. I'm gonna start with my task 1, what we are doing on it. First, we collect input and output data from the system. And then the input was the electrical power and the output is the temperature. We use the MATLAB to import the data from file called drive2. Then we remove the mean to center the signal. Then we select the range. Our range is range time from 0 to 0.08 seconds. After we select the range, we have like 1,000 data. We estimate, we divided it to 2 parts. 50% was for estimation use, 50% is for estimation from 0 to 500. This estimation, we use to build the model. And the other 50%, it's for validation. It's used to test the performance. And I will let my friend Mashfiq Mahmoud to continue for task 2.
Okay, Assalamu alaikum. Next slide, please. Next. Here. So I'm going to present task 2, which is more focused on stability and performance analysis of our system. So at the beginning, we get our transfer function from the task 1, and then we start analyzing the transfer function. So first we do our open loop analysis, and where we see that all the poles are left side of the S-plane, and that indicates that this is actually internally stable, but not efficient enough. So we do our step response analysis. Next slide. And there we get our rising time is 0.318 seconds, and then our setting time is 1.93, and the overshoot is 18.46%. And because of the overshoot, we can understand that the system is an underdamped system. And then we do our closed loop analysis, and with the controller, the system improves and the poles move more further left to the S-plane, and that indicates there is good improvement, and the rising time also become quicker, and then overshoot also become minimized. So that indicates that using controller actually make the system more efficient. Previous slide, please. Previous. Yeah, and we did our comparison here, the open loop system and closed loop pole zero map comparison, where we can see visually see the actual improvement because of the implementation of controller. Go to the next slide. Next. Yes, and this is our MATLAB code where we detailedly put finish our function. Next slide. Yeah, and this is task 3. My friend Mohammed will start.
Okay, thank you. My name is Muhammad Syaikun Razali, and I will tell you about the task 3, which is stability analysis, root locus, and board plot. The first one is the root locus. Root indicates that the system is marginally stable at gain k equal to 4.25. The stable range defined as 0, k less than 0, and k more than 0, but less than 4.25. So for the second, which is the B, from the board plot, previous slide. Okay, from the board plot, we use open loop system. So we can get the gain margin, which is 6.54 dB at 7.55 radian per second. And the phase margin is 57.65 degree at 4.76 radian per second. Next, we go to the next slide. So we go at the C, which is closed loop frequency response analysis. This we can get from the transfer function of the closed loop. We can get the magnitude peak, which is 1.54 at 3.72 radian per second, and the peak frequency at 6.36 radian per second, and the bandwidth, which is we can get from the negative 3 dB, we can which is the intercept at the transfer function of closed loop, and we get the 8.68 radian per second. So this indicates a fast and responsive system with slight resonance. Next. So this is the coding for the root locus, which part A, part B with open loop board plot and margins, and the last one is closed loop board plot. So I pass to the Nasir for the task 4.
Okay, Assalamu alaikum. Now I'm going to explain the task 4. For task 4, as you can see here in this photo, you can observe that branches of the root locus have shifted to the left. As you can see here, it has been shifted to the left along the negative real axis. This left shift is the key of improvement because it moves the dominant poles further into the left half of the S-plane. In control system, because we know that in control system, when it goes to the left, to the negative side, the system become faster and more stable. So for another important point is distance between the poles and the imaginary axis. With the PD controller, the poles are further away from the imaginary axis, which translate a higher damping ratio, which means the system oscillations smoother and more controlled transient response. Also, we can see the branches are symmetrical, and here you can see the branches are symmetrical. Also, the curve outward before converting back. The symmetry confirms that the system behavior remains back. It remains balanced and predictable as we vary the gain. Also, for the controller, we add a 0 at 6 equal to -6. And you can see its effect clearly because here we used -6. And you can see its effect clearly how the root locus bend this 0 pulls the root locus trajectory in a way that helps to meet our design goal for setting time and rise time and overshoot. And for the next slide is the coding for this task. Here, first of all, in this for the code, we define the Laplace variable. Here we defined the Laplace variable. Then for the G, we put the equation that we have, as you can see. And for the Z, it's here in this slide, in this area, for Z and PD and GPD. We defined the PD, and we used here 1 and Z, which means S plus Z, and Z here is 6, as we mentioned here, and the denominator is 1. And for the figure here, for this side of the code, the figure this slide here just to show the figure for the root locus. And then we obtain the value of k. Just for example here, we choose 0.5, and here the feedback closed loop transfer function. And this is for the coding. For the solution here, for this image here, it shows that the upper slide, as we can see from the graph, the PD controller significantly improves the system transit behavior. This rise is approximately 0.38, as you can see here, 0.318 seconds, meaning the system reacts very quickly to the input signal, which is very good. Also, the overshoot is only 4.21%, which is very minimal. This tells that the controller avoids excessive fluctuations beyond the target value. And most importantly, the system reaches steady state within 1.27 seconds with almost no oscillation. So now we move for the Simulink here. For the Simulink shown in this slide, for the Simulink, this block diagram represents the same closed loop system model using a PD controller in a simulation environment. We built this model to verify the performance in a more realistic simulation setup. The setup response output as shown in the scope block here in this block. Also confirms the same trend. There is a moderate overshoot and followed by a smooth setting. This suggests that the system is stable and well tuned. the oscilloscope here, the oscillation, sorry, the oscillation here seen is controlled by the feeds quickly, indicating the PD controller provides enough damping without requiring complex tuning overall. This Simulink response references what we observed in MATLAB. And for this graph here, the wave form in the scope block, we can clearly here see a smooth rise followed by a small overshoot. And here we can see this is the overshoot. It slightly went up a little bit, then continued stability in a stable way till the end. And that's it for my part. Now we go to task 5 with Mohammed.
Okay, thank you. So we go to the task 5, which is we use the Simuli model developed in task 4. So we click the PID block and then we tune the PID. So when we have the PID, we change the slide value under the response time and transition behavior. So we can look at the step plot, which is before tuning, the anti PID controller shows that the step response with high overshoots and slow settling. This reflects for damping and unstable tension behavior. So we have to change the behavior and response time, and then to tune and improve the accuracy and stability. Next. So by changing the slider value under the response time and tension behavior, we can look at the parameters. So we can compare the tune one and the block one. The block one is the old response, and the tune is the new response. So by changing the slider, we can get the overshoot that dropped from 32.3% to the 5.94%, and the peak response was reduced from 1.32 to 1.06 to minimize the oscillation. So overall, that the tune controller offered better accuracy and smoother transition performance. Next. So after tune, the PID controller improved the system behavior that much lower overshoot and minimal oscillation. And it also make a faster settling that compared to the initial ones. So I pass to the Sajjad to make a conclusion.
In conclusion, we know that the PID tuning efficiently reduce the overshoot and improve the accuracy of the system and make the system more stable. That's all for our group. Thank you.
Okay. Saja,
Yeah.
Amira of group 4.
What?
Can you explain to me
Mm-hmm.
the mathematical model for your case study from system ID?
Okay.
How many poles and how many zeros in
We
your?
have 3 poles and 1 zero.
Can I see?
Not it kind.
Go task 1, task 1. Show the transfer function.
The model.
Yeah.
ما هذا؟
This slide?
No, the number of poles and zeros.
This one?
The next one, you can zoom.
Where is the model?
The zeros in the midline and the 3 poles in the left.
The mathematical model, the transfer function.
We didn't upload it in the report.
Go to task 2, Nasser. In my one, I have in MATLAB. Next slide. Yeah,
This
here,
one?
here. Before the previous one. Yes. G equals to 96.84 over S cube plus 8.947 S square plus 57.03 S plus 99.04.
3 poles, no zeros. What is the best fit?
88.17.
88.17. Stable, eh? Mushfiq,
Yes, doctor.
what is the settling time and steady state error before controller design?
Before the controller design, go with previous slide. Previous one. It was 18.46.
18.46 second. Steady
Yes.
state error.
Yes.
Steady state error. Mushfiq, steady state
Yes,
error.
Oh, previous slide, Nasser.
Everybody should have one copy.
Okay, doctor.
Zero or have a value?
Have a value, doctor.
Have a value.
Because after the PID controller, it becomes 0, but before there was a value.
Share the codes. Can you share the codes? Any codes? Okay, stop. Bigger. Bigger.
Okay, 1 minute, Doctor.
Good.
Okay.
Kabir. Nasir.
حسنا.
Why there is a black square in my screen? Delete that. Delete the black square in my.
This one?
Yeah. Okay. Bigger.
Bigger.
Bigger. Oops. Slowly. Wait. Shah Ikhwan.
Yes.
Line 24. Line 14. Sorry. Line 14.
Line 14.
Up.
40.
14. 1-4. What is PZ map G?
Full zero mapping. Full zero mapping.
Benda tu.
Plotting the plot zero poles and zero.
Location of poles and zero on S-plane. Huh?
What?
Nasir Abdul. What is PZ map? 1-4. Line 1-4.
Line 14. BZ map is the pole zero map that shows the location of the system poles and zero for the complex plane.
S-plane.
Yes.
Yes.
Browse.
The G represent the transfer function.
I know. Browse down.
Scroll down.
Scroll.
Okay.
Next code. Next code. Oops. Nasir.
Yes, doctor.
T equal to feedback bracket K comma 1. What?
Yes.
1 stands for what?
1 stand for the feedback.
Feedback. What feedback?
There is 1 feedback.
Ikhwan? Ikhwan?
Yes. Unity feedback.
Unity feedback.
Hmm.
Scroll down.
Scroll down.
Next code. Next code. Next code.
This one.
Bigger. Bigger. Slope up. Wait. Scroll down. Scroll down. Scroll down. Okay, wait.
It's loading.
No. Bigger.
Okay.
Mashfiq, margin.
Yes, sir.
Margin bracket kg stands for what?
K is the gain and G is the transfer function, like the gain of the transfer system.
The gain of the system.
Yeah.
Astaghfirullahalazim. Saja, margin bracket kg stands for what? Saja Tambul.
Margin, we
Ah.
need to get like the K is we need to get our gain.
Astaghfirullahalazim. Nasir Abdo, margin bracket kg stands for what? In the
It stands for function that plots the board diagram.
Astaghfirullahalazim. That is BODE. This one is margin bracket kg. Last person, Shah Ikhwan.
Margin value of the transfer function.
Huh? Transfer function? Last chance. What is margin bracket kg? Last chance. Is the function to find gain margin, phase margin, crossover frequency of gain and phase. There, on the left hand side, GM, PM, omega CG, omega CP. Who wrote this program? Who wrote this program? Huh?
I am.
Sure, you type. You design. Okay.
Yeah.
To the right, Nasir. Go to the right. Go to the right, Nasir.
Go to the okay.
Okay. Feedback G title. Good. Yes. Nasir.
Yes, doctor.
What is Mac equal to squeeze? Mac. Squeeze. Mac.
Where?
Squeeze. There. Haza. Squeeze. SQU.
Squeeze here. This one.
Haza. Squeeze.
Yeah, squeeze used to remove singleton dimensions.
MashaAllah. Tabarakallah. Very good. Very good. Mashfiq. Max bracket meg. What do you mean by max bracket meg?
Where is it, doctor?
The next line after squeeze.
Okay.
Max bracket meg.
Nine.
Can you see?
Got it. Yes. Mine
Where
is
is
near
your
the
spec? Mashfiq, where is your spec? Supposed to
I
wear
s-
your spec.
yeah. The max magnitude is the maximum value, doctor.
Minimum value. Okay lah. Alhamdulillah. Finish. Thank you very much for your participation, anticipation. Okay, so can focus for final exam next Monday, inshallah. Happy Awal Muharram on Friday, inshallah. Make dua. And after Maghrib on the Thursday, make dua.
Make dua for us, we get full mark, Doctor.
Amin, amin, amin. Saja,
Okay.
make dua.
Inshallah.
Before Maghrib Thursday and after Maghrib Thursday.
Okay, inshallah.
Because after Maghrib Thursday is 1 Muharram.
Oh.
Before Maghrib Thursday is what? Zulhijjah? Nasir?
Yes, Doctor.
29, Zulhijjah.
Dhul Hijjah, after Dhul Hijjah,
After Zulhijjah is?
Muharram.
What is the last day of Zulhijjah?
29.
29. 29. 29 Zulhijjah. Thursday before Maghrib. Before and after make dua so that you pass excellent on Monday. Monday is the big war. Big war. Nasir,
Inshallah.
big war. Huh?
Inshallah.
Have you filled out EPPK? EPPK.
Not yet. I tried yesterday. The system was like down.
Yeah, error.
Error?
Yes, same here.
Yeah. Student portal is error.
Server error.
I will call the office to rectify the error. Thank you.
Okay, thank you, Doctor.
Thank you,
Thank you,
Doctor.
doctor. Assalamu alaikum, doctor.
Yes.
Assalamu alaikum.
On video, please. The last one. I don't know. Want to check? Because it's on. Okay, we're ready. Yeah, we're ready. Okay. You want me to check? Yeah. Only this. Yeah. Only this. Okay. I give you back tomorrow. See. Okay. Okay. Tomorrow. Hey. Cut your hair. Already. Cut your hair. Already. Internship. Riyad, on your video. Aris?
Yes,
Only three, eh?
there's one more.
Okay. Share slide. Riyad, where are you?
Okay, I can share the screen.
Are you in Saudi?
No.
I never saw you quite sometimes. Okay, Abu Bakar. Group number?
Group number 3.
Group number 3.
The last one. Model?
Yes.
Model?
Model C.
Huh?
C.
C. Okay, تفضل. تفضل.
All of us. Me, Abu Muhammad Abdul Halim, Muhammad Haris, Muhammad Nasir, and Riyad. Actually, Muhammad Nasir should be the one going to explain the introduction part. I think he joined. He joined. He waiting for you to get him in. He's waiting for you to let him in, doctor.
Okay. Okay. Approve. Proceed.
Okay.
Muhammad, on video. Muhammad Nasir, on video. Proceed, brother.
Muhammad Nasir, you can start.
I will start. I will do the introduction. Hello everyone. So our topic is about analysis of electrohydraulic actuator system. So electrohydraulic actuator systems are widely used in industrial automation due to their fast response and high power density and precise positioning capabilities. So our project focuses on modeling and control design of industrial standard hydraulic actuator using MATLAB. We aim to identify a continuous time model of the system through system identification techniques, analyze open loop and closed loop behaviors in both time and frequency domains, and design and tune PID controllers to meet performance specifications, such as minimal overshoot, fast setting time, and zero steady state error. Next slide, please. So we will be using system identification to build a mathematical models of dynamic system using measured data and having developed models to represent the relationship between input and output of the hydraulic actuator system. And then system identification procedures to include data processing, model estimation, validation, and analysis of system response, and tools to apply system identification, which involves MATLAB system identification toolbox to enable estimation of transfer functions and evaluation of model for performance through graphical and numerical methods. Next slide, please. We will be using a PID controller, which is widely used for control systems to improve stability, accuracy, and performance, where we'll be tuning the PID controller to achieve a desired system behavior. And PID tuner from the MATLAB, which is the effective tool to help automatically tune control parameters and visualize system response in real time and simplify the optimization process. Next slide, please. So our problem statement is, as we know, that electrohydraulic actuator systems are known for their high power density and precise motion control, and their performance is often challenged by nonlinear characteristics, parametric uncertainties, and system disturbance. So for accurate modeling and effective control strategies, it's essential to ensure stability and meet performance requirements such as minimal overshoot, fast response, and zero steady state error. So our project aims to identify the dynamic model of hydraulic actuator system using MATLAB system identification toolbox and design the optimized PID controller to enhance the system time and frequency response. Next slide, please. So our objective is to model an industrial hydraulic actuator system using system identification toolbox in MATLAB and to analyze the dynamic behavior of the open loop and closed loop system in both time and frequency domains, to design and implement PID controllers to improve system performance, including response time, stability, and accuracy, to tune the PID gains using Simulink PID tuner and compare the controller performance with classic tuning methods, and to validate and interpret system performance based on simulation result and control design criteria. Next, Mohammed Nasir will go with the scopes.
Okay, scopes. This project focuses on modeling and controlling an electrohydraulic actuator system, which is commonly used for process motion control. We use MATLAB system identification toolbox to create a mathematical model from experimental data. After that, we analyze the system's performance using MATLAB and Simulink in both time and frequency domains. Finally, we design PD and PID controls to meet performance targets like low overshoot and fast setting time. We also use Simulink's PID tuner to automatically adjust the controller for better performance. Next, please. Okay, limitations. Of course, there are some limitations. First, everything is done using simulation. No real hardware is tested. Second, the model doesn't include all nonlinear effects like friction or leakage. Third, controls performance depends on simulation accuracy and doesn't account of real-world disturbances. Finally, the tuning depends on the selected simulation settings and conditions. Next, please. Okay, methodology. The project followed 5 main steps. First, we defined the system using MATLAB and estimated a transfer function. Second, we analyzed the open loop system, looking at things like pole zero maps and step response. Third, we modeled a closed loop system and studied how gain affects stability. Fourth, we designed a PD control using the rule locus method. Lastly, we fine-tuned the PID control in Simulink to get the best response. And all steps will be explained in next slides.
Okay, I will take on from here. So for the first task, we started by plotting the voltage and displacement, which is our input and output for the system. As you can see here, the input signal is used to turn on the actuator, and the output is the output in millimeters, as shown in the figure right to the slides. And then this is the graph of input versus output signal. This is before we do any pre-processing or anything, before we even get into the system identification tool, which we get to on this slide. So is my mouse showing on the screen? Okay. Then we start by importing the data, which is the two files that we have for displacement, which is the output, and the input is the voltage. And then after we import, we'll start doing pre-process. Actually, before the pre-process, you can see the graph starts from 25. It doesn't start from 0. But after doing pre-process and removing the means, we can see the graph is starting from 0 here. This is the old graph in blue, and this is the new graph after doing pre-process. So this plot compares the simulated and the actual displacement response using the same input voltage. It confirmed the model accuracy by showing close signal matching. And here, after doing this, the pre-process, then we divided the system into two. As we know, we have like 1.5K samples. So we did the first 750 samples in this. Like we started from 1 to 750, and here from 751 to 1.5K. And then we drag and drop this the first data here in the working data, and the other one to the validation data. And then we did the time plot. This is the time plot. We have two plots here, as you can see. The plot in blue, which is represent the model's output, and the black one is the real data measurement from the actual file that we have. So as you can see here, it's not matching. Like there is some mismatch in the graph, and the best fit and the percentage. This percentage is it indicates the match between or the similarity between the actual measured output and the output based on the simulation of the model. So we can see we got 65.85 and a final prediction error of 5.05. In this case, our model has 3 poles and no zeros. So as we can see, it's like considered a low match. It's not that good of a match. It's not similar to the actual measured data. So we tried another time using 3 poles and 1 zero. Actually, we tried increasing the zeros because increasing a zero on the system, it improved the transient response. So as we added one more zero, we can see here we got 98% of fit estimation data, and then the final prediction error went from 5 to 0.015, which is quite low, and you can say it's a very good fit to the estimation data. This improvement suggested that the number of poles and zeros is suitable and accurate compared capturing the dynamics of the system. So yeah, this is the graph, and as you can see now, it's almost like identical or on top of each other because it's a good percentage. Yeah, that's it for the, and then after that we got the transfer function, which is, yeah, we end up with this one, 110.7s plus 2.94 divided by s cubed, 30.5 s squared, 0.688 s plus 0.126. So that's all for task one. We after using the system identification tool, we successfully obtained the transfer function, and then from here we can start on the task two. Then we started by finding the roots, which is I just used the command window. I defined g equal to the transfer function that I have, and then I plotted the root locus and the pole. It will be shown in the next slide. So after identifying the poles, it's like I identify this as an equation. Then I find the root for the equation. I get 3 poles, and I also did the same with the zeros. As you can see, the zeros are 110.7 and 2.54. Then I defined it here. Then roots q will give you the roots of the equation, which give me negative 0.0257. And then I plotted the root locus using this line here in the code, r locus d. Then after that, I defined zeta I did the 45-degree dampings, which gave us data equal to 0.707, which is, we'll give it this graph here. As you can see, it's 0.707, which is this actually done here by the line S grid, then zeta and 0. It will give you a line from 0 with the zeta angle. So from this, we obtain the gain equal to 6.6, and the dominant pole is negative 19.2, and damping is like 0.707, as I just said, and the overshoot of 4.3%. So we will go to the mapping. We map the poles and zeros. Okay, the previous part was using the command window. Now here I'm writing actually a MATLAB file. So I described I declared the transfer function, and then after that this is the transfer function after the feedback, which is g over 1 plus g, and then these lines here are the line used to display the poles and zeros. So as you can see in the graph here, this is pole, and this is another pole, and these two are zeros. And then I will get to explaining the other lines in a second. So this is the step response, which is generated by this line right here, which is step T. And then the title is step response, and on the grid, we'll get this response. This is before we did any modification, before we multiplied by the gain k. It gave us 0.6 rise time, and the settling time is almost is not existed in the graph right here. So it's considerably high value. This is the system specification before we have the gain k. As we get the ESS, the steady state error is 0.393, and then the other specification we can get from the graph here, the rise time is 0.6. Keep in mind these values because now after the gain k, this step response after applying the gain k shows the faster rise time and a small overshoot, indicating the improved response after multiplying by the gain k and doing the feedback. So as you can see, the rise time was 0.6. Now it's 0.07, which is way better. And then the overshoot is 5%, which is also considerably low. And then the settling time, initially it was like non available, and now it's like 0.2, which is quite fast, you can see. So these are the specification after gain K. You have like very fast rise time, transience time, anything is like quite fast compared to the first one. An overshoot of 5%, which is also considerably. It actually the overshoot is the only thing that like didn't improve, which is I think it's quite normal after multiplying by the gain K. Initially it was 4.4 and now it's 5.03, which is I think is quite normal. And then the ESS was 0.03, now it's 0.006, which is way lower. And yeah, that's it for the first three tasks. Now I will pass the mic to Paris. We'll explain the next two.
Okay, now we move on to task 4, which focuses on designing PD and PID controller using the root locus method. So this is the root locus that we generated. We got a gain of 4.2 and also a complex pole at negative 11.1 plus 12.5 J. So the damping ratio is 0.66 and an overshoot of 6.16. So the goal here is to ensure our hydraulic actuator system responds quickly with less than 10% overshoot, maintains stability, and achieves near zero steady state error. So next. So this is the coding that we use to generate the root locus. So the first one is the transfer function. And we use zero location at 5, which we want to make the root locus shift more towards the left to ensure stability and also a faster response. And then we multiply the PD with our transfer function. So that's how we got our root locus. Next. And this is the final step response with PD controller. So we selected a gain value of K 4.2 and also the 0 at 11. So dips help us push the pole further left, improving speed and also response. So the final closed loop system showed a faster rise time and also reduce the steady state error. And this step response confirmed better dynamic behavior with only, I think, 1.52 overshoot and fast setting. Next. So this is the coding that we used to generate the previous slide. Okay, I think next slide. And this is the PID controller that I generate using Simulink software. So we choose KP value of 18, KI equals to 6, and KD equals to 3. And this block diagram is the transfer function, but you cannot see the value because the number is too big. Okay, next. And this is the step response of PID control system. So the step response shows a fast rise with a slight overshoot and also a smooth settling, indicating effective regulation by the PID controller. Okay, next slide. So this is the open loop and closed loop hydraulic cylinder control system. So the open loop diagram shows a system without feedback where the desired displacement is directly used to drive the cylinder. So the closed loop diagram adds a feedback to the input to correct the errors and also improve accuracy and also stability. Next slide. So for task 5, we focus on automatically tuning the PID controller using the Simulink's PID tuner. So we use the Simulink model from task 4 and access the PID block to open the tuning interface. By adjusting the sliders for response time and transient behavior, we generated the optimized PID gains. So you can see this in the next slide. So yes, this is the interface. So we use the response time and also the transient behavior to make sure our spec is achieved. So as you can see, this one, the block response is the old, and the tune is we use this one to tune our graph. So we managed to get the overshoot percent. We managed to reduce the overshoot percent by 19.93%, which I think is meet the requirement. So yeah, I think that is all for me.
Okay, show me the model from the system ID. Okay, what is mathematical model? One zero three pole, correct? Model C.
Yes.
1034. Best fit? How much best fit?
98.09.
98. Okay, good, very good. Your presentation very good, no problem. Okay. Can I see the code, please?
Which part of the code?
Any code will do. Oops. Any?
Okay.
No, not this one. No, this is outcome. Okay. This there. Okay, next code. One locus. Okay, right. Next code. Next code.
No, that's it.
Very good. Okay, very good. Complete. So you, Haris, objective to reduce steady state error and to reduce settling time achieve, eh?
Yes, Doctor, achieve.
What do you learn from this assignment?
I think this assignment is like a process. For example, the task 2 is without the PD and PID controller. The settling time and also the ESS and also rise time is not so good without PD or PID controller. So to make sure that the settling time and also ESS is improved, we use PID controller so that we can get an overshoot and ESS to be reduced.
Abu Bakar Halim, from the assignment, what do you get on the positive side? What do you learn?
I learned how to use the software, like the system identification tool and all this MATLAB.
Never tried before?
No, the system ID tool and the PID tuner I never tried before.
Okay, good. Is it new experience to you?
Yes, the PID I've done some project with the PID before, but it was like it's not like this. This is more on the theoretical side. The one I've done is like it's already a written code, like a written function, and I just have to tune the PID by taking the parameters, the P and the I and the D, and then the output will actually like show you the real life difference of like tuning the P and like changing the values of the P. What will give you, what will affect, like the P will affect the instantaneous error, and then the I will affect the, like will sum up the past error and then try to correct it, and so on.
Okay, Muhammad Al Sharif. Nasir Al Sharif.
Yeah.
What do you learn, Nasir?
Actually, I learned like how to design and 10 PID and PD control to improve the system, which I can get less overshot and fast setting times, so we get better for performance for any control system that we use, which will make like it will be for our experience for the future when we work or something like that.
Okay. Riyad, okay, you have test at 5 o'clock, so I'll let you
Yes.
go. I'll let you
Okay,
go.
okay. Thank you, doctor.
Have you submitted the slide, Abu Bakar?
Yes, but I submitted as a link, like I submitted a PDF that have the link, and you click the link, will go you to the, will direct to the slides.
Your Google Drive.
Yes.
Email to me the slide.
The actual file.
Yeah.
Like because we used Google to like work simultaneously without that.
I need
But
a
okay.
PDF and PowerPoint file. Thank you very much.
Okay, thank you.
Subhanallahi wa bihamdihi, subhanallahi wa bihamdika, asyhadu an la ilaha illa anta, astaghfiruka wa atubu ilaik, wal asri innal insana lafi khusr illa alladhina. Thank you very much. Syukran Habibi. Terima kasih banyak-banyak.
Thank you, Doctor.
Thank you, Doctor.
Okay.